Hello, dear students. I hope you are doing well. In today's lecture, we are going to talk about rapidly varied flow. This is chapter 11 from our textbook. We already defined rapidly varied flow when we classified flow based on its variation by length. As you know, when we have sudden change in the water surface profile, as you see here, we will have a rapidly varied flow. There are two different reasons to have rapidly varied flow. One of them is, as you see here, is change in the flow bed or channel bed. This is a sudden change, a drop occurred here, therefore we have sudden change in the water surface profile and it creates rapidly varied flow. The other case for the creation of rapidly varied flow is change in the flow regime. For example, as you see here, a supercritical flow meets a subcritical flow here. Therefore, when a supercritical flow wants to change to the uh, super subcritical flow, there is a sudden change in water surface profile, which is called hydraulics jump. We already talked about it, but we will fully discuss the issue in chapter 12. So here we have rapidly varied flow as a result of change in the flow regime. And here you see the example of change in bed profile or river bed, which sudden change in the riverbed, a drop we have here. Therefore, we have sudden change in water flow surface profile, which creates rapidly varied flow. Therefore, in this chapter, we will consider change in uh, stream bed, and we will analyze variation of water surface profile. This is water surface profile as a result of change in the bed. Sometimes we can have a contraction in the bed, sometimes we can have a drop or a hump in the bed, some obstacle in front of a flow can change the geometry of the bed. Therefore, it they can create rapidly varied flow. And in this chapter, we totally consider this kind of the rapidly varied flows. However, for the case of hydraulic jump, we will discuss the issue in the chapter 12. Okay, now we are going to first talk about energy equation in open channels. Then we will derive required equation from the energy equation to solve rapidly varied flow problems, which is mainly determination of water surface profile in rapidly varied flows. Here you see energy equation for open channel flow. This is similar to the energy equation in pipelines that we already studied in fluid mechanics. From there, you remember we had such a formula, which is the Bernoulli equation plus the term of the loss of energy. However, you might not be familiar with the coefficient of alpha here that I will explain now. You remember Z1 was our potential head or the height of the point from the reference line. P over gamma is the pressure head, shows how much water is above the uh, point or above the uh, section in case of pipeline flow. And also we have a velocity head, which is equal to v square over 2g. And here alpha is the actually it is called kinetic energy correction factor, which is the rate of the or ratio of the kinetic energy based on actual velocity over the kinetic energy based on the average velocity. This factor is used to correct the assumption of average velocity that we use in energy equation. You know that in reality, velocity, if this is, for example, cross section at point 1, velocity at different point is different, and when we take an average and we assume average velocity here, uh, it includes some errors because average velocity cannot represent the real velocity of this cross section. You know that velocity at the walls and bed is 0, and by moving to the center of the cross section, velocity increases. Therefore, taking average will enter some errors, and to correct those errors we multiply the average velocity that we have. Average velocity, you see in these two velocities are average, that we multiply them with the kinetic energy correction factor. However, this is not a big deal in this course because we are dealing with turbulent flow, and in turbulent flow we can assume alpha equal to the 1, and therefore we sometimes can neglect both a1 alpha 1 and alpha 2 in the energy equation. um, okay, so let's come back to the our control volume. This is our control volume of non-uniform flow. This is a varied flow, gradually varied flow. Upstream depth is y1, downstream depth is y2, and you see that if we want to sum up the elements of total energy, we can add z1 to y1 to velocity head alpha 1 v1 square over 2g at section 1, and similarly at section 2 we should add z2 to y2 and also velocity head. And we if we consider head loss, which we will consider it in this case, the sum of all the terms will give you the total energy line. You remember this is total energy line, but when we uh, subtract the head losses from total energy line, we will have energy grade line between 2 points or between the input and output section of our control volume. This is energy grade line, and we know that the water surface profile is our hydraulic grade line, which is the summation of two terms. Yes, summation of two terms, P1 over gamma and Z term. And it should be noted here that we can replace Y1B with P1 over gamma if we assume the hydrostatic pressure in this point. By this I mean that here in point 1, the pressure equals to the gamma of the liquid, which is water, gamma times y1. Therefore, P1 over gamma will be equal to y1. One more thing in this slide we can mention is the bed slope. This is bed slope S0, and friction slope or slope as a result of the viscosity, which is SF. Here we can say that energy losses, head losses, equals to the, with respect to this length of the control volume L, we can use tangent theta equals to the front, to the side. Therefore, HL would be equal to the SF, or friction slope, times length of the control volume, or length of our river between two section, which is under evaluation. Okay, so as I told, pressure is, if we assume that pressure is hydrostatically distributed, we can replace P1 over gamma and P2 over gamma here with Y1 and Y2. Therefore, the energy equation in open channel flow can be shown in this way: y1 plus z1 plus alpha 1 v square over 2g equals to y2 plus z2 plus alpha 2 v square over 2g plus hl, head losses. And we talked about the alpha, which they are kinetic energy coefficient factor. Okay, here you see a case of uniform flow where the uh, water surface profile is in parallel with the bed slope, and therefore energy grid line is also in parallel with the water surface. So we can have a question like this: head loss for unit for uniform flow. So for the case of uniform flow, can you guess what is the value of head loss? I suggest you to pause the movie and think about it, and then come back to the answer. Okay, for the case of uniform flow, we know that in uniform flow we have y1 equals to y2, and therefore uh, velocity at this point equals to velocity at the second cross section. Therefore, what will be happen in this equation? In this equation, you can remove y1 because it equals to y2, and you can remove this term of v1 equals to v2. What will be remain? The remain is z1 e equals to z2 plus hl. Therefore, you can find HL will be equal to Z1 minus Z2. What was the Z1? Z1 is the height of the uh, bottom of the cross section at point 1 from our datum, and similarly Z2 is the height from the uh, uh, bottom elevation, or bottom height from datum at cross section 2. Now I'm going to divide both sides by the length of control volume, or control volume, which is from here to here, L. This gives you the head losses per unit length of the channel. Okay, so we can say that HL over L, which is the head loss per unit length of channel, equals to Z1 minus Z2 over L. Okay, and if you come back to the figure and look at the value of HL over L, which is distance between 1 and 2, it gives you this theta, yes? This angle of the inclination of energy grid line, yeah? Which is also equals to the uh, um, angle of inclination of channel bed, which we already denoted with S0, and for this case SF. And from here we can say that for the case of uniform flow, energy grid line, slope of the bed and friction slope equals to HL over L, and from here we derive that HL equals to Z1 minus Z2. Therefore, energy slope of the or angle of the friction slope equals to Z1 minus Z2 over L. Now we are going to repeat the previous energy equation for the open channel flow in case that the equation can be a bit more simpler than the previous, because here I assume that my datum crosses point 2. Therefore, what will be happen? Z2 would be 0 in my equation, and therefore I can write energy equation for this open channel flow like this: z1 plus y1 plus alpha 1 v1 square over 2g equals to uh, I don't have z 2. Therefore, I can start from y2 plus alpha 2 times v2 square over 2g plus hl. And we know that hl here is can be defined as the sf, which is this angle or this angle, times the l, which is the distance between two cross sections. So we can replace the term z1 z1 with a corresponding um, angle. You see here that z1 equals to s0 times l. Therefore, we can replace z1 with s0 times l. And also in this equation, we know the value of hl equals to friction slope times L. A new version of this total energy equation for the case of non-uniform flow with the assumption that Z2 equals to 0 can be given in this term. Uh, and as the flow is considered turbulent, we also assumed alpha equals to 1. Therefore, we will have such an equation for this case: y1 plus s0l plus v1 square over 2g equals to y2 plus v2 square over 2g plus sfl. You see that each side of this energy equation has three components, but two of them are so familiar with us: y1 plus v1 square over 2g, and here we have y2 plus v2 square 2g. Actually, the sum of the depths of flow plus velocity head is called specific energy, and we show it with E or ES. In fact, the specific energy is the total head above the channel slope. Why? If you consider this point, point 1, sum of y1 plus this value is the total head above the channel. And also for here, y2 plus alpha square over 2g is sum of the total head above the point. So this is called specific energy, and therefore we can, as you see here, yes, specific energy equals to y plus v square over 2g in any point in open channel flow, and it is called specific energy. If I replace the corresponding terms with E, this equation will be shown in this form. Instead of y1 plus v1 over 2g, I can say that specific energy at point 1 plus s0l equals to specific energy as point at point 2 plus SF times L. Therefore, this is the case that uh, my deuterium crosses the second point. Therefore, energy equation in gradually varied flow or even in varied flow don't it is not important or no matter it is gradually or varied flow. E1 plus S0L equals to E2 plus SFL. So here we see again the general form of energy equation, which is equal to y1 plus z1 plus alpha 1 v square over 2g equals to y2 plus z2 plus alpha 2 times v2 square over 2g plus hl. So in the channel bottom, we this is general form, yes. If the and we know that y1 plus v1 over v1 square over 2g is called specific energy. Assume that alpha is 1 for the turbulent flow. This is correct. And also for uniform flow, alpha would be 1 also. Um, if the channel bottom is horizontal, what will be happen? Z1 will be equals to Z2 because the channel bottom can be constant as a datum. You can cancel out Z terms from both sides. What will we have? From here we will have E1 and from here we will have E2. We already removed Z2 plus HL, and from the previous slide we know that HL equals to SF times L. So this is another formula that can be used when we are going to solve some of the problems in this chapter. E1 equals to E2 plus SFL. In other words, specific energy at cross section 1 equals to specific energy at cross section 2 plus uh, friction slope times the distance between two cross sections. This is the other case here. If the channel bottom is horizontal and no head loss, what does it mean? It means this is uniform flow. Yes, horizontal flow means you Z1 and Z2 is 0. And no head loss, when there is no head loss, you can remove HL term. What will be remain? It means that you can remove SFL from this equation or remove HL from this equation for the and the result will be E1 equal E2. When there is no head loss, when there is HL, what does it mean? It means friction, no head loss, friction slope equals to bed slope. Or in other words, it is definition of the uniform flow. Therefore, when we have uniform flow, energy equation in open channel is nothing than E1 equals to E2, or specific energy is constant along the channel. For the case of uniform flow, specific energy is constant. This is the other equation, very important and useful to solve a variety of problems in this chapter. Yes, here we have another equation and another example. This equation here E1 plus Z1 equals to E2 plus Z2 plus HL. In fact, this is the representation of energy equation with respect to the definition of specific energy. What I did, I only replaced y plus v square over 2g terms with e. Therefore, the general the general formation of energy equation in varied flow equals to E1 plus Z1 equals E2 plus Z2 plus HL. You know that when we remove Z terms, Again, we have the similar equation that I already explained. So uh, it is suggested to you that always know this equation, energy, specific energy at a cross section, which is the which is energy or total energy above the bed plus elevation of the bed equals to total energy above the bed at section 2 plus elevation of bed at section 2 plus energy losses. When there is no energy losses, we can easily remove HL. Therefore, this is the most general form. It should be memorized and um, will be very useful to solve the problems. And here you see that we have a horizontal channel with no head losses having sudden transition. Yes, this is a sudden transition. It is called hump. Therefore, it is the case of reasons behind rapidly varied flow. You see, this is a rapidly varied flow. Why? Because we have a change in the geometry of the channel, or we have a hump or increasing or sudden transition in the bed. How much it increased? It increased uh, equal to delta y. So as a result of this increase, what we expect? We expect that we have a rapidly varied flow. Here we assume that we have a rapidly drop or rapid drop on water surface. Therefore, before the hump, I can select one cross section, and after the drop, I can select another cross section. Therefore, between cross section 1 and cross section 2, I can write this general energy equation with respect to the energy, specific energy. Therefore, I can set that specific energy at this section equals to specific energy at this section plus loss of the head or head loss. So if I assume that this is my z, what will be happen in this formula, in this general form? Z1 is 0 because the datum is the bottom of the second. But I will have only a specific energy at section 1 in the left hand side of this equation. As you see here, I have only E1. At the right hand side, I have what? E2 plus Z2 plus HL. Okay, this is E2 plus what is the Z2? If this is your datum, Z2 equals to delta Y. Yes, I have delta Y plus HL. But you see here, the problem said that there is no head loss having sudden transition. There is no head loss, no no friction losses, no viscosity loss in this sudden transition. Therefore, I don't have a HL. Therefore, I can write a E1 equals to E2 plus delta Y. This equation can help me to find, for example, water elevation at above the hump. So this is also important to mention that um, also, I have a sudden change in the geometry. I neglect a kind of energy losses here, and that available energy loss is something similar to minor energy losses in fluid mechanics. You remember that in fluid mechanics, we divided energy losses in two different kind of energy losses. As you also see here, we had major losses and we had also minor losses. Major losses were those kind of losses which appeared as a result of friction along the channel or in fluid mechanics along the pipeline. For example, but minor loss was those kind of losses that as a result of sudden change in the cross section. Yes, for example, when we had a knee connection where we had a T connection in a pipeline, we assume that minor losses can be calculated with using the formula K times V square over 2G. So here also, if I assume this is my control volume, let's show you. If I assume my control volume is something like this, yes, therefore length, the term L that I have here is too small and negligible. This is why we can neglect SF times L, this term HL, when we derive the. Yes, when we derive this equation, we can neglect the uh, loss of energy as a result of friction because L is too small. However, we will have minor loss because of the such a sudden change in the geometry of the cross section, but it is also negligible. Therefore, we can solve some similar problems using this expression that specific energy is constant along the channel. If you have a thumb, you should consider that specific energy at second section will increases with the value of the height of the hump. Okay, let me summarize this chapter or this section, and then we can see some examples in next lecture. We said that energy equation in open channels can be calculated using this formula. Each of these terms are an element of total energy in open channel. Summation of water depths plus kinetic energy is called specific energy. And for the case of uh, varied flow, specific energy plus uh, height of the bottom of the channel in section 1 will be equal to the specific energy at section 2 plus height of the channel at section 2 plus the head loss if we have. If we do not have head loss, we can remove this term. And for the case of uniform flow, we saw that, and in horizontal flow, specific energy at section 1 will be equal to specific energy at section 2. Okay, this is all for this lecture. I will solve some examples for this chapter in next lecture. Have a good day.